In this short video, we'll look at Harold's 1D simulation of a Fabry-Perot laser cavity. What we see here on the screen already set up is the epitaxial layer structure with the 3 quantum wells in red. In the device node is where we define the length of the cavity, the width, the reflectivity of the mirrors, and a few other parameters. And then in the simulator node is where we define what type of simulation we want to do and for which current range. So first, let's do an isothermal simulation. This corresponds to the laser in a pulsed operation. And it takes a few seconds to get started, and you'll notice in the top right the green wheel is spinning. At any point in time, we can click that to halt the calculation. Okay, so after the simulation is done, we can click the Inspect button and look at various results that have been calculated. First of all, let's look at the various densities, the electron and hole densities in the quantum well and the bulk regions, and we'll plot them all on one graph. And you can see here that the confined electron and hole densities are approximately the same, but there's a slight unevenness in the distribution in the quantum wells. Let's look at the versus bias results. We can plot things such as optical power versus bias. So optical power output versus the current. And other things too, such as the lasing wavelength, where we can see it settles down, once we reach the lasing condition, settles down to around 855 nanometers. And of course, other things as well, such as the modal gain, again as a function of current. We can look at the spectra tab and plot things as a function of wavelength, such as the gain versus wavelength, change of refractive index, and spontaneous emission. All very useful quantities to study when designing a Fabry-Perot laser. Next, we can switch to a self-heating mode and redo the calculation. And this will allow the inclusion of the thermal effects. So like before, it'll take a few seconds to get started, and you'll notice the wheels turning green at the top right. Again, we can click here to halt the calculation if we wish. So we're seeing a similar Li curve as we did before, except for the fact that now we see some sort of thermal roll-off. So again, we'll click the Inspect button. We'll go straight to the versus bias results and plot the active radiant temperature. And definitely, as the bias is increased, the temperature in the active region increases quite dramatically. This is due to the fact that the top contact has resistance, and also the fact that the heat sink in this model is defined to be at the bottom below the thick substrate, as opposed to on the top closer to the main source of the heat. Therefore, there's a significant temperature rise in the quantum wells. We can plot a few other factors too, such as the lasing wavelength. And certainly that's not as stable as it was previously, again due to the heat. Optical power at either of the facets or just total power. That's what we saw on the graph here. And again, quantities such as the modal gain. Which in this case is stable. Other things can be included in this long list, such as spontaneous emission, AlGaA recombination, etc. Again, all very useful quantities when designing a Fabry-Perot laser.